Hello, everyone. Hope you're having a fantastic day today. It's going to be a good day. Got my pink pencil. We're ready to go. Today, we're going to be talking about definite integrals. Now, before we get into this, I just want you to know something up front. On this first lesson, we are not going to be actually computing definite integrals using our integral rules. Instead, what we're going to be doing here is we're going to be understanding the idea of what is a definite integral. All right, so to start us off here, it's a very simple concept. If you travel at a constant rate of 40 miles per hour, how far will you have traveled after 1, 2, and 3 hours? And if you see, I've got my 1, 2, and 3 hours marked off on T. And then 40, constant rate of 40, my velocity is graphed on Y. I want you to think about this for a second. Back in physics, how did you discover distance? How did you discover distance? Well, you take your velocity and you multiply it times time, right? Distance equals rate times time. I wrote that over here for you. Or your rate is your velocity. So if your time is 1 and your velocity is 40, then over here, so after 1 hour, we've got 40, this is miles per hour, and that is times 1 hour. Then your miles per hour, your hours here will cancel. You end up with 40 times 1, which is 40 miles. If you're confused about the hours canceling, let me do it again with 2 here. After 2 hours, you've got 40 miles per hour, maybe this will help, times 1 hour, and your hours, since you're multiplying and dividing by hours, will go away. And, oh, I'm sorry, this is 2. 2 hours here, you've gone 80 miles, right? 3 hours later, it's 40 miles per hour times 3 hours is equal to 120 miles. Hours go away, you're left with miles. Okay, now, this 40, this 80, this 120, if you're looking at this and you're multiplying time times velocity, think about this in a geometry standpoint. If I cut this little piece of my graph up, 1 times 40 gives me 40, right? That's kind of like saying the area under the curve between 0 and 1, so 1 by 40, gives you your distance. 1 hour, 40 miles an hour, gives you a total area here of 40 miles. Do it again, you have 40 times 2, that'd give you 80. 40 times 3, that'd give you 120. So I'm going to write this off to the side here. The area of these rectangles represents, reps, the distance traveled. So the area under this curve represents your distance traveled. That's pretty cool, isn't it? All right. Now, what's the relationship between velocity and, well, you know what? I'm going to save that question for after we do this one. Okay, I want you to just do this real quick. This graph right here, represents reps total distance traveled. I'm going to come back to what I was going to say after we do this one. Hopefully this will be a little bit more clear after we do this bottom one here. What does the graph below describe? Okay, so now we've got velocity, but now our velocity is changing. All right, it's changing here. So it's still the same thing. The area under this curve is still going to represent how far I've gone, right? This is kind of like saying, what happens if it's changing or if it's going 2 or 3 units out, right? Now, straight off, I don't actually know, I don't actually have any values for x. So I'm just going to make something up real quick. This is just as an example. Let's say that this point right here happens at 2. So 1's over here, 3's over here, blah, blah, blah. So say it goes from 2 to 4. Those are nice even numbers. If you look at what's happening here, I still have a rate. If you remember, we talked about this when we first introduced velocity. Velocity is speed. The only difference is velocity has direction. So this is a positive speed. This is a negative speed. In other words, you're going backwards, right? Or excuse me, positive velocity, negative velocity. You're going backwards here, but you're still speeding up. So kind of think of it that way. So this graph, since you actually have a negative value here, we're kind of thinking instead of distance, because distance is positive, this is going to represent displacement. And remember, there's two different things between distance and displacement. Distance is how far you have gone, period. Displacement is how far have you gone from the origin, from where you started. So this graph, this represents displacement. Technically, the one above it does too. It's just everything was positive, so I didn't worry about it. So if you wanted to use this, if you wanted to find out how far you'd actually gone, all you'd have to do is say, let's say that this is the area of 1. All right, they'll call this section 1. So this will be A1. This will be A2, area 2. All right. So the area of 1 is 1/2 base times height. So it's a length of 2 on the base, a height of 40, or excuse me, length of 2, height of 40. Times 40, which is 40 miles. So you've gone 40 miles one way, and then 40 miles the other way, right? 1/2, 2, and negative 40, since you're down here, over 2, down 40, well, that's going to be negative 40 miles. If you're talking about distance, then you're just an average of 40, right? So let's talk about displacement and distance here. Your displacement, find how much you went this way, find how much you went this way. So it's going to be A1 plus A2, which is 40 plus negative 40, 0. Now again, this is displacement, right? Distance traveled, though, you just add up the absolute values. So distance, this will be the 40 plus the positive 40, which is 80 miles. And again, this is distance. Just explaining the difference between distance and displacement here. Again, this all has to deal with the area under a curve, and that's the big picture that I want you to look at. The area under the curve. Now, what I want to look at up here, I'm going to go back up here just real quick. What I'd like to look at, what's the relationship between velocity and distance? Well, distance comes from position, right? Distance comes from position. Position is s of t. What's the relationship between position and velocity? Well, velocity is the derivative of position, right? So I could write it like this. If you take the derivative of position, s prime, you're going to end up with velocity. So what if we started with velocity and wanted to go backwards? We would integrate, right? we do the antiderivative. That's what we've just done. We've just done an antiderivative by finding the area under this curve. Now that's kind of abstract, so flip the page over and it's going to explain it here. I'm going to explain it. It's going to explain it. Come on. Definite integrals can be interpreted as the area between the graph of y and the x-axis, and between x equals a and x equals b. This is how a definite integral is written. The way that it's read, the integral from a to b of f of x dx. Now what this does here, this says, this guy right here, says to find the area between f of x and the x-axis. And you're going to find it from x equals a to b. That's what a definite integral does. A definite integral finds the area under a curve. Now again, I'm not going to show you how to do it just yet. I'm not going to show you how to actually find the definite integral. As far as numerically, I want you to understand what it is graphically first. If you can understand what a definite integral is, what it does, then finding it numerically is no problem. So just as an introduction, we are only going to use it as like a tool to understand what it does. So we've got an equation here. The integral from -2 to 1. So I know it's going to go from -2 to 1 of x plus 2 over 3. Okay, I don't like the way that that's written. So the first thing I'm going to do is rewrite it. Integral from -2 to 1. And I'm going to change this to 1/3 x plus 2/3 dx. That way it's slope-intercept form, and hey, I can actually graph that. So let's graph it. Sitting here talking about it, let's do it. So we've got, I'm going to need my ID for this. We've got a y-intercept of 2/3 and a slope of 1/3. So it's going to be right here on the y-axis, and a slope of down 1 over 3, down 1 over 1, 2, 3. Okay, now that's actually going to hit my graph. If I go up 1/3 and over 1, that's actually going to hit my graph right here at -2, 0, -2. And let's draw your graph here. And let's continue it until it runs out of space. So again, the integral here is going to be the amount of space that's going to happen between these two graphs. All right? So let's see what happens. I'm going to go from -2 to 1. So let me zoom in on here so you can actually see what I'm getting. From -2 to 1. Well, here's 1. And I want to find, just as light as I can, I guess, that area. That's what this question is asking. All right? I want to find that area. I want to try and figure out what is the area using that information. So let's set it up. I'm going to look at the shape. Well, the shape is a triangle, right? The shape is a triangle. So what I'm going to do here is come up with just my regular 1/2 base times height. So the area, or excuse me, the integral, this is going to equal 1/2 My base here, it looks like it's going over 1, 2, 3. My height, what is that hitting at? 1? Is that actually hitting 1? If it hits here, it's up 1 over 3. Yeah, it's actually hitting 1. So it's a height of 1. So 1 times 3 is 3 times a half is 3 halves. So it's 3 halves, or 1.5. So the area under the curve is 3 halves when evaluated from -2 to 1. That's all it's asking here. It's simply asking you to figure out what goes from a -2, or excuse me, what's the graph doing from -2 to 1? All right. Now, this next one's a little bit trickier because it goes from 0 to 4. This one was a triangle. -2 to 1 is a triangle. This one is going to be a little bit trickier because it's the same graph, but now we're going from 0 to 4. So now this piece that's under here, let me see if I can erase that. It's not going to be there. Instead, I'm going to integrate from 0 to 1, 2, 3, 4. So now I want to find this area. I should have drawn my line a little bit better because it's up 1 and over 3. So it is actually coming and hitting at 1, 1, and up 1 over 3 will put you at 4, 1 as well. I did not draw that very well. Matter of fact, let me fix that right now. Otherwise, that's going to bug everybody. Okay, that's much better. Up 1 over 3. Much better. So I should have established that at the first. I'm sorry. If you're going through 2/3, if you're starting at 2/3 and you go up 1/3 and over 1, that's the same slope as going up 1 over 3. So you're at 1, 1 is a good point. 1/3, because if you put 1 in for x, that's 1/3 plus 2/3 is 1. Same thing for 4. 4/3 plus 2/3 is 6/3, or 2. So my apologies for not making that a little bit neater. Should have, didn't. I apologize. So this one is going to go from 0 to 4. And again, I am using my limited amount of information to try and come up with some kind of a set, or some kind of an area to fit under this thing, right? Now it's an odd shape. That shape's actually a trapezoid. So I've got 2 methods of doing this. I can bust this thing into a couple of different pieces if I wanted to use triangles. It's going to be kind of messy, but that is an option. One option would be to find the area from this point over, like find the area of this triangle from -2 to 4, and then find the little triangle here and subtract it. That's one area, or that's one possibility. Let me show you that one first. So this will be using triangles. It goes from -2 to 4. So now my base is 1/2 6 units by 2 units tall, right? From -2 to 4, that's 6 units there by 2 units tall. It's kind of hodgepodge together, but I just want to really drive home that a definite integral is all about area, okay? And then the little area I found back here, the little piece from -2 to 0, that's going to be 1/2 this little white piece right here from -2 to 0. Again, I'm so sorry about that line. It hits 2. It just looks really bad. but it does hit 2 right here at 0, negative 2 comma 0. So my unit is 2 here and 2/3 up, so 2 2/3. All right, and that's one area. That's one way to find just the area of the shaded region there. Find the area of this big old triangle here, then find the area of the little one, get rid of it. The other option is that you could actually use the trapezoid. All right, I want you to look at the shaded area really quickly. The goes from here 0 to 4, right? Goes from 0 to 4, and then it goes from 4 to 2 over here, or excuse me, 4 comma 0 to 4 comma 2, up to 2/3 right here. So yeah, this is okay. I can do this. If we're going to do this, we'll have to use a trapezoid formula. Let me back up just a hair here. So this is using a trapezoid. If you haven't known, or if you've forgotten the formula for area of a trapezoid, it's 1/2 your base, which in this case is 4, times the height of both of these right here. Technically it's 1/2 height times base times base plus base, but that's irrelevant. These guys right here, I'll need to add them together and multiply that by 1/2 times 4. So it's 1/2 and 4. The bases are the two parallel sides. So in the formula anyway, the bases are the two parallel sides. So it's 2 plus 2/3. Let me write this off to the side. The area for the formula of a trapezoid is 1/2 height times base 1 plus base 2. Your bases are your parallel sides, just in case you were wondering. Those actually come out to be the same values, these two equations. All right, and then the last one here, I know that this is kind of getting long, but the last one, I promise, goes from -5 to 4. Okay, so let's come up here and let's shade in this one. So -2, 3, 4, 5. Here's -5. And I am looking at this entire couple of bits here. So I want to find the area. So what I'm going to have to do is bust this into two pieces. All right, so first, I'm going to need to figure out the area between -5 and -2. So I'm going to need to bust this up, -5 to -2 of the equation. And then I'm going to need to find the area from -2 to 4. So see, it kind of goes -5 to -2, -2 to 4. So everything is taken into account. The only thing that's changing is I'm breaking it into two pieces, so it's a little bit more manageable. All right, and then that's going to be, it's a triangle, so thank goodness for that. 1/2. Your base is 3 units. Your height looks like, what would that be here? 1 down -1. I really need to draw this better. This line's all kind of jacked up. Whew, okay. Over 2, down 2. It does actually go through this point right here. I am so sorry. It's probably getting a lot harder to see this just because of my horrible graphing. But if you plug in a -5, you get -3/3, which is -1 rather. So it does go through -1. All right, and then plus we've got from -2 to 4. So it's going to be 1/2 unit of 6, and it goes up 2, which is -1.5 plus 6, 4.5, 4.5. Now again, because you have Oh, wow. Because you have places both above and below the graph, let me back up here. I want to just note again, this represents displacement. So if you can forgive my horrible graphing skills, we will be okay. Again, I am so sorry. It just went crazy. That's all right. All right, y'all have a good one. We'll talk about this Monday.